So let us start the problems on moving charges and magnetism. The first problem is as follows. A proton is moving northwards with a velocity of 5 into 10 to the power of 6 meter per second, huge velocity, in a magnetic field of 0.1 Tesla directed eastward. Find the force on the proton. Now, we first need to picturize the given problem. So, according to the given problem, what we have here is a proton moving northwards. So, we need to make a diagram of directions. So, if I call this as north, this as south, this will be our west and this will be the east, right? And according to the given problem, the proton is moving northward. So, at this point, let us assume that the proton is here and is moving northwards. So, this is the direction of velocity, right, whose magnitude is 5 into 10 to the power of 6 meter per second. And at this point where the proton is moving, we also have a magnetic field of 0.1 Tesla directed eastwards like this. So, this is the direction of external magnetic field B. How much? 0.1 Tesla. And now we need to calculate the force on the proton. This is the given situation. So, this is the direction of B according to the problem, and this is the direction of V. Angle between them, we can observe that it is theta is equal to 90 degree. The formula for the force experienced by a moving charge F is equal to, it's only about magnitude of force that we are asked to find. Just a minute. Okay, so it's only about the magnitude of force which is asked to find, which is equal to QVB sin theta. Okay, so what is theta? Theta is the angle between V and B. So according to the diagram, we can see that theta is equal to 90 degree. What else is the given data here? We have Q given, the charge that is moving. The particle that is moving is a proton, and this proton will have the same charge as of an electron, but positive. So, the charge that is moving here is 1.6 into 10 to the power of minus 19 coulomb. The velocity with which it is moving is also given, 5 into 10 to the power of 6 meter per second, and the magnetic field in which the charge is moving is also given, which is 0.1 Tesla. Right? We have all the factors required to get the value of force. We can substitute them and get the value of force. So, it is 1.6 into velocity 5 into 10 to the power of 6 into magnetic field 0.1 into sin 91. Okay. So, simplify that using the calculator, and hence we will get the force is equal to 8 into 10 to the power of minus 14 Newton. 8 into 10 to the power of minus 14 Newton. This is the total force experienced by the proton. And now, if you are asked to find the direction of force, what will be the direction of force? V cross B will give you the direction of force, right? What is V cross B? V cross B, right? V cross B. So, the direction of force is into the board. So, the proton is pushed into the board like this, okay? So, it will go like this into the board, okay? So, that is about the first problem, very easy one, right? The next question is as follows. A circular coil of 20 turns and radius 10 centimeter is placed in a uniform magnetic field of 0.10 Tesla normal to the plane of the coil. If the current in the coil is 5.0 ampere, 5 ampere, what is the total torque on the coil, total force on the coil, average force on each electron in the coil due to the magnetic field? Once again, let us visualize or keep the diagrammatic representation of the problem. So, it is a circular coil of 20 turns and radius 10 centimeter. Okay. So, it is a coil of 20 turns. Okay. Capital N is equal to 20. The radius of the coil is 10 centimeter given. Keeping it in meter, it is 10 to the power of minus 1 meter. Is placed in a uniform magnetic field of 0.10 Tesla. So, this coil is placed in a uniform magnetic field of 0.1 Tesla in such a way that, okay, the direction of magnetic field is given here, the magnetic field of 0.1 Tesla normal to the plane of the coil. Okay. See, this is how the magnetic field is normal to the plane of the coil. If this is the plane of the coil, this is how the field lines are. Okay, normal to the plane of the coil. So, this is B, the external magnetic field, which is how much? 0.1 Tesla. R is given, B is given. Okay, now current in this coil is also given. Okay, current in the coil is 5.0 ampere or 5 ampere simply, right? 5 ampere current is flowing through that, right? That's it. Those are all the given data, and we also have finally the area of cross section of the wire is just given here. It is 10 to the power of minus 5 meter squared. Area of cross section of the given wire is 10 to the power of minus 5 meter squared, and n, small n, the free electron charge density. Okay, free electron density, number of free electrons per unit volume, small n, that is also given. Okay, which is 10 to the power of 29 per meter cube, right? Okay, so now we have all the given data, and now we should get the values of these things. First one is total torque on the coil. Again, the expression has to be mentioned. It is tau is equal to, remember what is tau is equal to? The total torque experienced. Electric torque is P cross E. Similarly, magnetic torque is M cross B. So, it is MB sin theta, the magnitude of torque experienced. But now the question is, what is M? M is the magnetic dipole moment of the given coil. Okay. What is the direction of magnetic dipole moment here? The direction of magnetic dipole moment, if we assume that the current is flowing like this out of the board here into the board here, then the direction of magnetic moment is same as of the external magnetic field like this. If we assume, since the direction of current is not mentioned, we can even assume that the current is flowing in the opposite direction, into the board here, out of the board here. Even then, the direction of M will be like this. In both the situations, theta is either 0 degree or 180 degree, right? If I consider this one, theta is 0 degree. If I consider this, theta is 180 degree. So, assuming both the situations, for any situation that I consider, sin theta becomes equal to 0. So, sin theta becomes 0, and hence the total torque becomes 0. But you must mention the unit of torque, Newton meter. 0 Newton meter is the torque experienced by the current carrying coil of 20 turns. Okay. Next is total force on the coil. Okay, see, total force on either electric dipole or magnetic dipole in the external field is always 0. Okay, if I take electric dipole, positive charge experiences certain force, negative charge experiences certain equal and opposite force in the dipole, electric dipole, and hence the total force becomes 0. In the same way here, half of the coil, okay, half of the coil experiences certain force in one direction, the other half of the coil experiences force exactly in the opposite direction, but the magnitude of force is equal, right? They are pulled and pushed with the same amount of force, and hence the total force or the net force on a current carrying loop due to the external magnetic field, current carrying loop due to the external magnetic field is always how much? 0 Newton. Okay, that's it, very easy. Equal and opposite force on half and one half and the other half of the coil, and hence the total force is always 0. Okay, keep that in mind. So we have answered two of the two parts of the question. Let me go for the third part. And the third part of the question is as follows: average force on each electron of the coil. See, here is the coil, and each electron is experiencing certain force. Because see, the direction of electron, okay, the drift velocity's direction itself is the velocity, drift velocity itself is the velocity of the electron, nothing else. So this is how the electron would be directed, tangential to the line, isn't it, the circular path. So this is V and this is V, angle between them is always 90 degree. Right? You try to imagine. If I consider the coil like this, then an electron, if the flow of current is taken like this, then the electron would move like this. So at this point, the direction of velocity of the electron is tangential to the path like this, right? And what about the magnetic field? There it is given that magnetic field is normal to the plane of the coil. So which means it is somewhat like into the board or out of the board, okay, like this. So this is how the magnetic field is, and this is how the velocity of each electron is. Angle between them is 90 degree, okay. Before that, average force experienced by any moving charge due to the external field, okay, is F is equal to QVB sin theta. We know that, right? Force experienced by any moving charge in the external magnetic field is F is equal to QVB sin theta. Now for this particular case, what is theta equal to? Look at this, B is into the board, V is like this, so theta is equal to 90 degree. And since it is electron which is moving, which then constitutes for the current, then that is why V, the velocity of the charge, is nothing but the drift velocity of the electrons. Because drift velocity is the velocity with which all the electrons will be drifting in the given coil or moving in the given coil. So V is equal to Vd, right? What is Q equal to? Q is equal to charge of an electron, which is 1.6 into 10 to the power of minus 19 coulomb. What is B? B is given 0.1 Tesla, right? So in order to get the force, we have Q, B and theta, but we do not have Vd. We should first obtain Vd and then substitute back into the expression. How do we get that? Look at this. We are given with the current in the circuit, 5 ampere. So I is equal to 5 ampere, and we have an expression for current expressed in terms of Vd, right? I is equal to NEA Vd, isn't it? Now out of this expression, we can get the expression for Vd and that would be equal to Vd is equal to I by NEA, right? So that becomes equal to I is 5 ampere. What is N here? N is this free electron density or charge density, 10 to the power of 29, 10 to the power of 29 into what is E? Charge of each electron, which is 1.6 into 10 to the power of minus 19. What is A? A is the area of cross section of the given wire, 10 to the power of minus 5 meters square. Simplify this and you will get the value of Vd. Okay. After getting the value of Vd, you put that into this expression and get the value of F. Okay, you should do that. F is equal to Q. Here you have Q. Vd you take it from this. B you have here, theta is 90 degrees, so sin 91. Simplify and get the value of force experienced by each electron in the coil, which are moving with the velocity of Vd. Okay. So, third question, when a straight conductor of length 0.2 meter, 0.2 meter carrying a current of 1.2 ampere is placed in a magnetic field of 0.3 Tesla, it experiences a force of 3.6 into 10 to the power of minus 2 Newton. Calculate the inclination of the conductor with the field. This is one part of the question. Next, find the force if the conductor is at right angles to the magnetic field. So, initially the conductor is of certain inclination. This is how the current carrying conductor is. Okay, we can assume that the field is somewhat like this. Okay, this is what is B and this is what is our L. Okay, the length element through which we have a current. Okay, vector L, the magnitude of vector L is 0.2 meter. The magnetic field value is 0.3 Tesla. 0.2 meter is the length of the conductor, which is placed in the external magnetic field of 0.3 Tesla, right? And current flowing through the conductor is also given how much? 1.2 ampere, right? It experiences a force. Force experienced by this conductor is also given how much? Force experienced is F is equal to 3.6 into 10 to the power of minus 2 Newton. So now we need to find the inclination. Inclination means nothing else. We need to calculate theta, angle between L and B. Okay, how much inclined it is with respect to the magnetic field. So there is given data and the formula is also known to us. Force experienced by a current carrying conductor, a straight current carrying conductor in the external magnetic field is F is equal to, it is I of L cross B vectorially. Writing the magnitude part, it is going to be I L B sin theta, right? What is F? F given is 3.6 into 10 to the power of minus 2. What is current? Current is 1.2. What is the length? 0.2, which can be written as 10 to the power 2 into 10 to the power of minus 1 into what is B? B is 0.3 Tesla, which can be taken as 3 into 10 to the power of minus 1 into sin theta, because we need to find theta. That's it. Okay, look at this. LHS is 3.6 into 10 to the power of minus 2 is equal to so if you simplify this, 1.2 into 3, okay, 12 3s are 36. So it is going to be 3.6 into 2 into 10 to the power of minus 2 into sin theta, right? And now you have 3.6, 3.6, same factors getting cancelled, 10 to the power of 10 minus 2, 10 to the power of minus 2, same factors getting cancelled, and hence we will be left with sin theta is equal to 1 by 2. So if sin theta is equal to 1 by 2, what should be theta equal to? Sin inverse of half, which is sin inverse of 0.5. So theta is how much? 30 degree, right? So, the conductor is inclined 30 degree with the external magnetic field. That is how you should keep the answer. Okay. Therefore, the given conductor is inclined 30 degree with respect to the given magnetic field. That is it. We have the value of theta obtained. Next, find the force if the conductor is at right angles to the magnetic field. So, this is another situation where the same magnetic field is considered, same conductor is chosen. This time the conductor is carrying the current right angles to the magnetic field. Okay. So, for this situation theta is directly given 90 degree and asked to find the value of force. When theta is equal to 90 degree, the expression simply becomes F is equal to ILV. So, current is 1.2 ampere, length is 0.2 meter, magnetic field is 0.3 Tesla. So, the force becomes equal to how much? Simplify this. This is 2 into 10 to the power of minus 1, 3 into 10 to the power of minus 1, 6, 12, 6 are 72. 7.2 into 10 to the power of minus 2 Newton. This is the amount of force that the conductor will experience if the conductor is kept right angles to the external magnetic field. Okay. So, this is about third question. 2 parts. Both the parts are answered. Right. The next question. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field. Calculate the magnitude of magnetic field. So, here we have, let me draw the diagram here itself. Here we have a wire of mass 200 gram and length 1.5 meter carrying a current of 2 ampere. It is suspended in mid-air. Okay, this is how the wire is. Okay, of length L is equal to 1.5 meter. Mass of the wire is 200 gram, which is 0.2 kg. Right? And it is suspended in mid-air. Right? It is stationary. It is in mid-air without any support. Okay? But if you want such an arrangement where any body is suspended in mid-air, there should be an opposing force or an opposite force for the weight of the object. Because when you suspend it in mid-air, gravity always pulls it down. Weight of the body is always downwards. So, we need an equal and opposite force for this weight in order to suspend it in mid-air, right? What is the force that we are observing here? The force that we have here is the magnetic force. So, suspended in mid-air by a uniform horizontal magnetic field. What kind of horizontal magnetic field do we have? The magnetic field that we have here, okay, if you just think of horizontal, suddenly you will get the feel that okay, magnetic field might be like this. No, here the magnetic field is not like this. Instead, the magnetic field is horizontal, it is not vertical, but it is not in the plane of the board. Instead, it is somewhat like entering the plane, okay, or leaving the plane. Let me look at it. So, it is L cross B, which will give us the force. So, since this is L cross B, okay, L cross B should be the force. So, B should be into the board, right. So, this is the external magnetic field in which the conductor is kept. Okay, horizontal, yes, it is horizontal, not vertical, but it is out of the plane, or it is entering the plane, it is not in the plane. Okay, fine. So, you have mass of the wire given, length of the wire given, horizontal magnetic field. Yeah, now we need to calculate B itself. B is equal to question mark. Now, considering the condition of freely suspended situation, freely suspended way, here weight should be balanced by magnetic force, right? W, weight of the object, should be balanced by the magnetic force. Weight of the wire is mg. So, mg is equal to magnetic force, which is I L B sin theta. What is theta here? Theta is 90 degree. Okay, this is how the, it can be anyhow, but we'll take theta as 90 degree. The problem is, in fact, the problem is incomplete. Okay, but we can consider theta as 90 degree for the simplification of purpose. So theta is 90 degree here. Mass of the wire given is 0.2 kg. Let us take G as 10 is equal to current through the wire is 2 ampere, right? Here it is, current through the wire I is equal to 2 ampere. So it is 2 into length of the wire given is 1.5 meter. Magnetic field shall be found. That's it. You have all the given data to find the value of magnetic field, right? 10 into 0.2, 2 is equal to 2 into 1.5 into B. 2 and 2 cancels, B is 1 by 1.5, which is, here it is 3 by 2 comes here, becomes 2 by 3 and hence 0.66 Tesla. This is the magnetic field in which the current carrying conductor is kept so that it is freely suspended in mid-air. Okay. So the basic thing is balancing weight with the magnetic force. That's it. Rest everything is known to us. Okay, the next question and the last question of the session. An electron, after being accelerated through a potential difference of 100 volt, enters a uniform magnetic field of 0.004 Tesla, perpendicular to its direction of motion. Find the radius of the path described by the electron. So this is about radius of the path prescribed by the electron in the external magnetic field. We already have the expression for the radius of the path, right? The radius of the path is expressed as R is equal to mv by qb, right? How do we get that? qvb is equal to mv square by r, and hence we will get this. Okay. So R is equal to mv by qb, this is the radius expression. Here, do we have m? What is the particle chosen? The particle chosen is an electron whose mass is known to us, 9.1 into 10 to the power of minus 31 kg. So fine. Do we have q? Q is charge of the electron. Do we have the value of that? Yes, we do. 1.6 into 10 to the power of minus 19 coulomb. Do we have the value of B? Yes, we do. 0.0004 Tesla. Right? M, mass of electron, 9.11 into 10 to the power of minus 31 kg. V, don't know. V has to be calculated. V is not directly given. What about Q? Q is equal to charge of electron, which is 1.6 into 10 to the power of minus 19 coulomb. So we have all the factors given here, but not the value of V. So let us find V. Is there a method to find V? What is given? The electron is accelerated through a potential difference of 100 volt, which means when the electron gets accelerated through a potential difference of 100 volt, it gains certain energy, certain kinetic energy, isn't it? So that gain in kinetic energy of the electron is half mv squared. From what energy is this kinetic energy is coming here? So the loss of potential energy itself is converted into this kinetic energy. Loss of that potential energy is EV, where E is the charge of electron, V is the potential difference in which or through which it is accelerated. So using this, I can get the value of V, right? The expression for V becomes equal to EV, which is 100 volt, E is known to us, okay, it is 2 EV, okay, 2 EV by M under root of it, okay. So under root of 2 EV by M is what is the expression for V, the velocity, right? And now what we actually need is R, okay. Let me see, substitute the value of the expression of V into this expression of R, okay. Even you can get the value of V there, Okay, simplify for V and then put the value of V here and get the value of R, that's also fine. Or else you can simplify it directly like this, since the value of V is not asked. If the value of V is asked, you should calculate V and then put the value of V into this. Okay, so R is equal to M by QB into, what is V? V is under root of 2 EV by M, right? So now look at this, M and M shall be cancelled, it is root M, no? So one of the M remains in the numerator. Yeah, what is Q? Q is E itself, right? Charge of electron. So 1 by B remains inside, and inside the braces M, the M by E goes into the square root and becomes M, okay, 2 M V, the potential difference, 2 M E, because one of them gets cancelled, divided by one of the E will remain in the denominator by E. So you simplify these values there and you will get the radius in which the electron will remain. You do the calculation, make use of calculator, that's fine. Okay, so this is the 5th question. Okay, we shall discuss more problems in the next session. Thank you.